So today we'll be talking about regression models. These are typically very simple machine learning models that we can use to fit a line to a curve. So regression typically requires an independent variable and a dependent variable, and it's basically just trying to find where these two match and how they relate to one another. So let's use a real example. Let's say we're looking at plants and how the amount of water influences the growth of the plant. We have our independent variable, which is the water, and the amount of water is something that we can control. We have, of course, our control, and that's everything else, so that could be the amount of soil, and we want this to remain constant throughout. Otherwise, if we have too many changing variables, we don't quite know what's actually correlating to our data. And then we have the dependent variable, and this is how much the plant is growing, and this is what we're measuring. A regression model would look at this data and we would be able to plot the independent versus the dependent. So how much water is being introduced and how much the plant is growing. And hopefully we could see some sort of linear relationship or any sort of relationship between the plant itself and how much water it has and what it grows to. So the first regression model we're going to be looking at is linear regression. Linear regression is one of the most simple regression models. It's essentially just calculating a line equation to best fit your data. So let's say we're calculating how the years of experience influence your salary. So we'll have an equation which is going to be your salary, and salary is the variable we're calculating. This will be some sort of intercept, so beta 0, and then that's going to be added to beta 1, which is the slope, multiplied by the years of experience, plus some sort of error term that can be calculated. You might recognize this equation as y equals mx plus c, because this is a simple line equation, and that's all we're doing here. We're plotting our data and we're trying to find a line that best fits in between it, so we can look at how many years have you done and where your salary should lie. So let's use this data set. This is completely, well, not completely random, but we've made it up because there's quite a range of £10,000 to £70,000. And of course, this doesn't accurately reflect wages. So this data is what we'd use to train our model. So firstly, we calculate the mean of both our x data and our y data. To calculate the slope, we get the covariance between x and y. This is how much they move together, and we divide it by the variance. This calculates the slope of which fits our data. Then we want to look at the very minimal value. So this is where our line intercepts the y-axis. Now y-axis is our base case. So given 0 years of experience, what would be the wage that we have? And that's how we calculate the line. It's that simple. So let's say we're doing something more complicated. We might be trying to calculate the cost of a house. Now we might think the size of the house is going to influence the cost of it, but that's not always the heuristic we can go by. Sometimes it might be the proximity to a school, or it could be the square footage of the land around it. So let's pick just two variables to make it simple. We're going to look at the size of the house and how close it is to a school. Now we've got two variables going in, rather than just the one like we had in the previous example. We want to now predict our y label, so that's how much does the house cost. So instead of just having on a two-dimensional plot cost versus size, we now have a three-dimensional plot. So now we have a three-dimensional plot. On our x and z, we have the data, our independent variables. This is how big the house is and the proximity to a school. And then on the y-axis, we have the cost. And we're essentially plotting a line, not just on the 2 dimensions, like in the previous example, but all across the 3rd dimension to work out the boundaries of how these variables interact and where it lies in 3-dimensional space. Now, when we adjust the equation, it looks very similar to the previous one, but instead of just having one gradient, so that's our B1, we instead are multiplying it across lots of different gradients. So this is essentially having loads of different line equations going across to represent the 3 dimension. So the final regression model that I'm going to cover is logistic regression. Now despite its name, it's more of a classification algorithm than it is a regression model. This essentially takes in data and it has something called weights. So this weight is basically assigned to each input, and the value of the weight basically works out how important each input is. and then we apply something called an activation function. So typically this will be the sigmoid function, and all this does, it caps the data between 0 and 1. So what we do here, let's say we have an image going in to the regression model. It will take in each pixel, apply some sort of weight to the pixel, and that goes to an output. And then we can cap the output to a 0 or a 1, depending on what the input is. And this is how we do a binary classification task. So let's look at a more interesting example of regression models. Instead of having loads of different variables, let's say we're taking an entire image, and that image is me right now. What we could do with that is train a model to predict facial landmarks. So this is all the points on my face. And this can be used for all sorts of algorithms, and it typically is used even on your phones when you're applying filters. It's working out interesting points on my face, and it might decide to add sunglasses based on the points of my face. Now, when we put that in a regression model, a lot of the data going in is completely useless. Like the background information here, we don't need in the model. But what we do want is my face, because that's what's useful for the model to detect where these different points are. So the regression model is a really simple approach to this. Many would probably use like a neural network or something more complicated, but regression models can even do it because there's a spatial element that the pixels within the middle or wherever my face is are usually going to be, and of course if the color is a certain or the shade is a certain value, then it will work out well, I think this is about where the face is and this is where the point should be. So it can be used for some quite complex tasks, and we don't always need to have one output like in the previous examples. As you can see, we can have many different outputs because it's predicting the coordinates of my face across a larger area. So it doesn't just have to be the cost of a house as your output. You can do some really quite interesting things. So in today's video, we've looked at regression models. We've covered a few different examples of this and how we can take singular data or multiple data and predict something quite interesting out of it.